Hi there, I am Parth, and I welcome you to a talk on my work titled Investigating Visual and Tactile Associations in a Ponerine Ant Diacamma indicum using pupae as a motivation. Let's begin with a fundamental concept of learning. What is learning? Now, various definitions of learning exist, but one that encompasses all its aspects has been more or less elusive. A more Catholic definition of learning, which was proposed by Bemer, is that learning constitutes attention, concentration, and effort. It comprises an animal gradually changing its behavior through experience, a change that decays in absence of that experience. Out of the different forms of learning, associative learning has been one of the most extensively studied. Associative learning occurs when an organism learns to associate an event or a stimulus with another event, which can be a reward or a punishment. Associative learning has been observed in many insects, including those shown here. What we'll be focusing on today is associative learning in ants. Ants live in a wide range of ecological niches like rainforests and deserts. Here, they must learn sensory cues coming in from different faculties like touch, vision, and olfaction, along with idiothetic or self-motion cues to survive. Now, for insects like ants, particularly those that forage solitarily, vision, touch, and olfaction are important for navigation outside the nest, where it must navigate towards a goal. Within the nest, touch and olfaction are more important when moving around in darkness. Naturally, many species of ants, including wood ants, species belonging to the Myrmica genus, and Cataclyssus cursor, have been shown to use visual cues for associative learning in the context of foraging and navigation. Tactile associative learning has also been studied, although very less extensively, in the species Lasius niger and Cataclyssus fortis, to the best of our knowledge. Interestingly, tactile learning was only found to be true in Cataclyssus fortis and not in Lasius niger. This study focuses on studying associative learning in vision and touch in the model species Diacamma indicum. A brief introduction to Diacamma indicum. It belongs to the family Formicidae and the subfamily of ponerine. It is a primitively eusocial ant, and the reproductive individual is called the gametes. Nests are subterranean with sizes ranging between 12 to 261 individuals. Previous studies in this species have shown that visually impaired colonies could successfully relocate using tactile cues, although the transportation time is slower. They can use natural landmarks near the nest entrance, which, when displaced, affects the path efficiency of tandem running pairs during relocation. And antennae, which are used for tactile sensing, when restricted, increase the relocation time and the number of interruptions of tandem running pairs. These studies, along with the sensorily rich natural environment Diacamma lives in, indicate the importance of vision and touch for the species. But to the best of our knowledge, there has been no work on visual and tactile associative learning in the species. So our objectives for the study are, can Diacamma indicum learn to associate visual cues with a reward? Can it learn to associate tactile cues with a reward? And finally, if the objectives 1 and 2 are true, then does there exist a preference for tactile and visual cues for association with a reward? Now, all associative learning studies require a motivation to allow training an individual to learn a cue. So what do we use as a motivation here? Food has been the quintessential source of motivation in learning paradigms for many animals. Similarly, relief from a negative stimulus like escape from water or electric current in rats has also been used as a motivation. Praise and petting have served as motivations in animals like mice and dogs. We observed that with Diacamma indicum foragers lose motivation after the colony has been satiated. And there's no guarantee that a specific individual will make multiple trips to allow us to condition it. Light can act as a negative stimulus for colonies during relocation to a new nest, but relocation is a colony level activity and not an individual one. So conditioning one specific individual is not feasible. And finally, we don't know how to praise or pet an ant. We wanted a motivation that could help us overcome these limitations and still be ecologically relevant. Now, the life cycle of holometabolous insects like Diacamma indicum comprises 4 developmental stages: egg, larva, pupa, and adult. The first 3 stages are brood stages that ultimately give rise to the adults. Brood is a prized possession of insect colonies. It is a means to achieve reproductive fitness. Larvae can act as reserves of food in insect colonies by exudating nutritious fluid. It can also be cannibalized when food is scarce. The importance of is highlighted by the fact that in nature, many ant species are involved in slave making through brood raids and theft. In Diacamma indicum, it has been shown previously that workers prefer brood rescue even during the emergency of relocation and also involved in opportunistic brood theft from a conspecific colony. Out of the brood that they steal, they prefer pupae. They are the worthiest since they need least investment in terms of rearing before they close into adults and become part of the workforce. Given the importance of pupae, we tried to use pupae for motivation for our experiments. We saw that using pupae helped us overcome the problems with conventional rewards. There was no loss of motivation as the training proceeded. If anything, there was actually a gradual increase of motivation and quickness with which the ants took the pupae. Also, multiple trips between the nest and the reward were guaranteed. Therefore, we decided to use pupae as a motivation for our experiments. So the setup consists of a Y maze connected to the nest box. The ants come out of the nest box to the decision area. Here they choose between two arms with different cues. On the end of both the arms are pupae, but only at the end of one of the arms they're accessible. The cue where the pupae are accessible is called the condition cue, and where they're not accessible is called the non-condition cue. On the right side is an example of a training run. So the ant comes out of the nest box, comes to the decision area, and decides between one of the cues. It goes the length of the arms, and if it finds a pupae, it grabs one and takes it back to the nest box. Now, after each of these training runs, the arms are randomly flipped. They are wiped with ethanol, and the pupae are balanced on both the sides. The first experiment involves testing if the ants can visually associate a reward with a cue. On one arm, I put white dots on a black background, and on the other, I put black dots on a black background. During the training, I flipped the arms randomly, as mentioned before. During the test run, I removed the pupae and placed the arms randomly and record the total time it spends on each of the arms. If the ants can associate the visual cue with the reward, it should ideally spend proportionally more time on the conditioned visual cue than the non-conditioned cue. So what do we get? The proportion of total time spent is significantly greater on the arm with the conditioned cue, conditioned visual cue than the one with the non-conditioned cue. In more specific terms, it was about 1.6 times more on the conditioned cue than on the other cue. Hence, associative learning of visual cues was achieved. For the tactile association experiment, we used an 80 grit sandpaper as the rough surface and the backside of the same sandpaper as the smooth surface. In the experiment, they were actually painted black. Here, they have been painted white to give a qualitative sense of how rough the surfaces are with respect to the ant. The bottom panel shows the qualitative difference in the surface topographies measured using a surface mechanical profilometer. The RA value is the average of the individual measurements of deviations along a surface. The RQ measures the root mean square of the distribution of the surface deviations from the mean line on the surface. Same as the visual association experiment, the tactile cues are placed on the two arms. One of them is the condition cue. The ants undergo 10 training runs followed by a test run, where the time spent on each of the cue is recorded. If the ants can actually associate the tactile cue with the reward, it should ideally spend proportionally more time on the conditioned tactile cue than the non-conditioned cue. We observed that the proportion of total time spent is significantly greater on the arm with the conditioned tactile cue than on the one with the non-conditioned tactile cue. Quantitatively, it was approximately 2 times on the conditioned relative to the non-conditioned cue. Hence, we can conclude that associative learning of tactile cues was achieved. The final experiment involves finding which cue, tactile or visual, the ants prefer when faced with a conflict between the two. During the training runs, we paired the cues as shown here, black dots with black smooth surface and the white dots with black rough surface. We trained the ants to associate either of the pair with the reward. Here, the ants are rewarded on the side with the white dots on the black rough surface. However, during the test run, the cues are recombined to result in a conflict. Black dots with black rough surface and the white dots on black smooth surface. Now, if the ants prefer to spend time on the side with the white dots on black smooth surface, that would imply that they prefer the white dots, which is the visual cue. If the ants spend relatively more time on the side with the black dots on the black rough surface, it would mean that they prefer the tactile cue. 24 ants were trained with the cue combinations shown here, and an equal number of ants were trained with the recombined cue combinations, which is the white dots on black smooth surface and the black dots on black rough surface. We observed that the proportion of total time spent is significantly greater on the arm with the conditioned tactile cue than on the one with the conditioned visual cue. Quantitatively, it was close to 2 times on the conditioned tactile cue relative to the visual cue. Hence, tactile cues are preferred over visual cues when placed in conflict. Okay, so the key takeaways here are pupae can serve as novel and ecologically relevant source of high motivation for sustained terrain durations in learning paradigms. Visual associative learning is possible in Diacamma indicum. We provide evidence of tactile learning in Diacamma indicum and a rare evidence of tactile associative learning in ants in general. We also show that ants prefer tactile cues over visual ones when they are placed in conflict. I would like to thank Professor Sumana Annagiri for the immense support and the latitude she provided me to explore different paradigms during the experiments. I thank Mr. Basudev Ghosh for collecting and maintaining the ant colonies and present and past members of Behavior and Ecology Lab. I would also like to thank IISER Kolkata and the Indian Science and Education Research Board for the generous funding and the British Ecological Society for providing me the opportunity to talk about my work. Thank you for your attention. I hope you enjoyed the talk. If you have any questions, you can email us directly or put them up on the platform, and I'll try to answer them as soon as I can.